Hey, grade 9, welcome to the second part of topic 3, which is all about resistance and Ohm's Law, which is kind of our first work in a while dealing with some calculations. We're going to get into that today. And you're even going to be manipulating an equation as well. So this is getting quite mathy, but hopefully that doesn't upset you. And let's get into it. So first of all, let's talk about what resistance is. We've talked about it a bit already. I think I've mentioned resistance a few times, but resistance is the property of a substance that hinders movement of electric charge and converts electric energy into other forms of energy. So the analogy when it comes to like water is resistance would be if there was like a thinning of the pipeway that the water is going through. And as a result, the water would slow down and less would be able to make it through. The water would lose some of its energy, right? And then less would be able to make it. So as I increase resistance, well, I'm losing some of my energy, my voltage, and current as a result will be lower. So that's really the idea behind resistance and how it works. If you go to kind of the idea of the water wheel that we talked about with the water model of electricity before, viewing it as water, you would think about a water wheel as if it were in the pipe. It's like slowing down the water as it goes through, and it's converting the energy from the water into another form by the wheel moving. So that's the idea. That's what resistance is. It's resistance to the flow of electrons. So remember that in an electric circuit, voltage, current, and resistance are very closely related. So again, brief descriptions of what everything is. Current is the amount of electrons going through the conductors, right? So it's a measure of how many electrons are traveling through a point in a circuit every second. Voltage is the energy that the current has or the electrons have. So the potential energy of the power supply is why the electrons move through the circuit. The higher the voltage, the more the electrons want to move. And then resistance is the kind of opposite almost. It's opposing the motion of electrons. And it takes away energy from the electrons when we have resistance and converts it into other forms. So to properly understand resistance and resistors, this is a good time to talk about conductors and insulators. Conductors conduct electric current very easily because of their free electrons. So as a result, they have very low resistance. So in a conductor, electrons are free to move around from place to place. They're not tied tightly to their material, so they can move more freely, which means there is less resistance. So think about it as a very large, unclogged pipe. Well, an insulator opposes electric current and makes poor conductors. When you have an insulator, it holds its electrons very tightly. The electrons cannot get through very easily, and so as a result, they have very high resistance. It would take a massive voltage in order to get electrons to go through them. So let's kind of do a quick activity and see where things would be. I'll give you a few examples, and then this being an ed puzzle, you can come up with some of the other ones. So poor conductors, again, mean that they have very high resistance. Electrons cannot move easily through them, while good conductors mean that it has a low resistance. It's an insulator. Oh, sorry. I totally said that wrong. Poor conductors are insulators, and they have a high resistance. So electrons can't move through. Electrons are tied very tightly. Well, in good conductors, electrons are more free to move and they have low resistance. So here we have our insulators and here we have our non-insulate or our conductors. Wow, I'm super confused by the fact that I have this reversed and that's causing me all sorts of issues. You know what? Let's just move it right now so we don't continue that confusion. So we come to glass. Is it a bad conductor or a good conductor? Well, it's an insulator. It's a bad conductor. So in glass, electrons are held very tightly, so it does not conduct electricity very well. If I had something like silver, that would be an example of a good conductor. And as you learned in chemistry, when I have metals, they are good conductors. Wood would be another example of a bad conductor. Well, something like gold would be a good conductor. What about plastic? Where would plastic be? That's right, plastic would end up being a bad conductor or an insulator. Air, also bad. bad conductor. It's an insulator. Electrons are held very tightly. What about aluminum? Where would aluminum sit? And that would be a good conductor. It's a metal. So in all metals, electrons are not held very tightly. They are able to move. So that would go to the good conductor side. For copper, that is also a good conductor. And finally, rubber would be a bad conductor. So I think most of you probably just know this a little bit from life, understanding what would be a good and a bad conductor of electricity. But again, we call bad conductors insulators, and they have very high resistance. So electrons cannot easily move through them. So the symbol for resistance is the ohm, and this is very massive, but that is the unit for resistance, which is the omega symbol, and that is our unit for ohms. Our symbol, though, our variable for resistance is R. So here's the formula, which is called Ohm's Law for calculating resistance. Resistance of a circuit is equal to voltage divided by, just dropped my binder there, voltage divided by current, voltage being our potential difference. So all we have to do is take whatever we have for a voltage, divide it by the current going through the circuit, and we have found our resistance in ohms. So given the fact that voltage has the unit of volts and current has the unit of amps, an ohm is really equal to a volt per ampere or amp. I can even get fancier, not that you need to know this at all, but I think it's just kind of neat to see. If we go to our very, very basic units, I know what a volt is equal to. It's a joule per coulomb. We covered that kind of earlier, I believe. And then when we talk about amps, that's a coulomb per second. So I have here a joule per coulomb and a coulomb per second. I'm not sure how much you've learned about in math with fractions and stuff, but this would be the same as if I multiplied both of these together with one being flipped. So that means that I would have a joule, what am I doing? Joule second per coulomb squared. Yeah, weird unit, but it is what it is. Okay, let's go ahead and get into some examples trying out this this formula. But actually before that, let's talk about manipulating this. So don't worry about this unit stuff. That doesn't matter. Just care about the fact that resistance is in ohms. Now let's try to manipulate this to find voltage and to find current. If I were trying to find voltage, I wanted to isolate this. I can get rid of the I by multiplying both sides by I to get voltage alone. You always do the opposite to what it's doing in the equation to get rid of it. So because I'm dividing by I, let's multiply both sides by I. And that ends up getting the formula for voltage of V is equal to I times R, because then this would go away. Well, what if we wanted to find current instead? We wanted to find I. Well, then in that case, we would divide both sides of this by R to cancel it out, and I would have I is equal to V divided by R. So this now gives us three different forms for this formula, right? That we can use to solve for different things. So if I want to solve for resistance, it's V over I. Voltage is I times R. And then for current, it's V divided by R. I like using this format, this formula. And then that one's really easy to manipulate because whatever I want to solve for, right, I just divide by the other thing. So if I want to solve for current, I divide both sides by R. If I want to solve for resistance, I divide both sides by I, and I'm off to the races. So let's try an example. Let's go through the process. We're going to go through 4 examples here and try them out, and let's see how it goes. So I have here 3 volts is applied across a 6 ohm resistor. What is the current? So the information I have is I have my voltage, which is equal to 3 volts. I have my resistance, R, which is equal to 6 ohms. And I have my current, which is what I'm looking for. So I'm going to start out with this form of the formula just for kicks, V equals IR, which is the one that I have in my head, okay, that format. And then let's manipulate this to solve for I. So if I want to solve for I need to divide both sides by R, divide by R, and I get V over R is equal to I, which means that I is equal to my voltage, 3 volts, divided by my resistance, which is 6 ohms. And I end up with a current here of 0.5 amps if I divide 3 by 6. Let's go to another example. An electric motor is connected to a 9-volt battery. If a current of 0.20 amps is flowing through the motor, what is the resistance of the motor? So let's talk about what we have. We have a voltage of 9.0 volts. We have a current of 0.20 amps, and I'm solving for my resistance. That is my unknown. Try it out. See if you can find the resistance. So here's the solution. V is equal to IR. So if I want to solve for R, I'm going to divide both sides by I. So R is equal to V over I, which means R is equal to 9.0 volts divided by 0.20 amps, which means that I have an answer of 45 ohms. I can show that to you in a calculator, but I mean 0.2. If I'm dividing by 0.2, that's the same as multiplying by 5, which is how I did that in my head. 9 divided by 0.2 gives me 45 ohms. All right, so that's that question. Let's do another. Example 3. This is all you. You try this one out and then look at the solution and see if you're correct. So here's the information I have. I have a voltage equal to 6.0 volts. I have a current equal to 0.50 amps, and I want to find my resistance. So I'm going to start with the same V equals IR formula. Again, I feel like this is the easiest to manipulate, so if you're going to have one form, this is the one to have. Let's divide both sides by I to get R by itself, so that will cancel out. And I end up with V over I is equal to R. So resistance is equal to my voltage, 6.0 volts, divided by my current, 0.50 amps. And my answer for this is 12 ohms. I'm just realizing now that we haven't talked before about the problem-solving process that you should go through when you're doing problems like this, or any problems in science that involve numbers. This is the process I want you to go through, where you first write down all your variables, which you have and what you're looking for with units. You write down your original formula, okay? Then you plug stuff in to your formula with units. So I'm plugging in my values and writing the values instead of the variables. And then I write my final answer, again, with the proper unit. Last question. What is the resistance of an electric heater if a current of 12.5 amps runs through it when it is connected to a 120 volt wall outlet, which is the voltage that comes through outlets in your house? Try it out. And here's a solution. Current is equal to 12.5 amps. My voltage is equal to 120 volts. And I'm looking for my resistance. So V is equal to IR. I want to solve for resistance, so I'm going to divide both sides by I. So I have V over I is equal to R. So my resistance is equal to 120 volts divided by 12.5 amps. So my resistance at the end of the day is equal to 120 divided by 12.5, 9.6. So I have 9.6 ohms. Okay, moving on. So let's talk a little bit about the component called a resistor. So there actually is a electronics component called a resistor that you'll find in almost any circuit, and what it does is it simply just resists current, and as a result it allows control of voltage and current through that branch of the circuit. So resistance, again, is the property of a substance that hinders motion of electrical charge and converts electrical into other forms of energy. Providing resistance in a circuit can be a desirable thing, as it can be used to control current or voltage in a circuit to meet the needs of devices. And how it does that is resistors simply convert energy from electrons into heat energy. So resistors get hot, and they're just built to actually withstand heat and basically dissipate it throughout the circuit. So this is a big reason why when you're dealing with computers and stuff, they get hot, is because of the resistance within the computers, and that's why they need cooling and so on. So normally a resistor contains a heat conducting core to absorb the heat generated by the conducting material. And this is actually just showing you a resistor and how hot it's getting being hooked into a power supply. It's just a resistor without the outside coating. So kind of neat to see. There are even resistors that are called variable resistors or potentiometers, something like that. But variable resistors can change their resistance. So anything that's like a knob will be a variable resistor. And by turning that knob, you are actually changing the resistance of that resistor. So when you think about like a volume knob on a stereo or something, that's actually what it is. Okay, as you're changing the resistance, and that's why it gets louder as you turn it, because you're lowering the resistance. Okay, you're making it so a higher voltage can make it to the speakers. Well, if you end up turning it to have higher resistance, less current, less voltage makes it to the speakers, and as a result, it gets quieter. So these can be used to control the resistance, which will change the current and voltage that reaches the device. For example, dimmer switches and lights. When you have a dimmer switch, it's the same thing, right? The slider type or the one where you turn, it's the same idea. It's actually just changing the resistance. So how that works is we have a material that has some resistance, and then as the knob turns, the slider changes so that it contacts in a different point. So you can imagine if the wire is attached here and then here to the slider, as this turns further and further away, as it turns in this direction, resistance is going up because it has to go through more of this resisting material, which is typically some kind of carbon that provides resistance. And so the further I go, the more resistance I have. But all you need to know is that variable resistors are just resistors where resistance can be changed. So let's talk quickly about house wiring. We're almost at the end here. Houses are wired so that if one device is turned off, other devices will still work, which means, and we talked about this before, but devices are connected in parallel. When you look at the lights in your house, the outlets, everything else, those are all connected in parallel. So the voltage or energy of the electrons is the same in all the branches. However, when additional devices are turned on, overall current from the power supply increases. So the voltage doesn't change, but the current will increase. So that's why typically, I know that sometimes this happens, but when you turn on lights, it's not like other lights dim. You might be thinking, well, sometimes when I plug something in, the lights do dim. That's because you're drawing so much current with that device. So things like heaters and vacuums and stuff is drawing so much current from that device that less current can go through the other channels. So that's a power supply issue. It's not an issue of the voltage dropping. But yeah, in houses, parallel circuits, which means that the same voltage is reaching every device. Last thing is talking about breakers. A circuit breaker or a circuit fuse just actually limits the current that can get through. So how circuit breakers or fuses work is that as current gets too high, it will trip, or the breaker will trip, or the fuse will burn out. And what that means is that it basically opens the switch and cuts current going through that circuit. So it cuts power to all the loads that are on that breaker or that fuse. So this prevents current from getting too high if there is a short circuit or something, which means that you have two wires that are basically directly connecting to power without any resistance in between. So the current would be super high, or if somebody was getting electrocuted, right, that sort of thing, then the current would be too high and the breaker would end up flipping. And then as a result, the electricity would turn off. So this is a safety device to prevent things like fires, electrocutions, that sort of thing. But that's what a breaker does. It's really just a fancy switch where it trips the breaker as soon as the current gets too high. So you have like 5 amp, 15 amp, 10 amp breakers, 25 amp breakers, depending on what devices are going to be plugged into that area, okay, so that it doesn't trip too easily. But then once it does have too much of a current going through, the circuit will open, and yeah, then you got to reset the breaker. Okay, well, that's it. Have a good rest of your day.